need for high voltage. Let's just have a look at this video. I'm going to try put it on repeat. Can you all see the video first of all?
Yes, sir, we can see it.
Right. So what we're actually looking at here, right? You would have seen those all over the place, whether they're on towers that look similar to this or on towers that look similar to or bigger towers. Those are conductors that actually transmit or distribute high voltage around like an area or between two areas. So that's what's carrying the electricity. That's what's carrying the current. So you'll see these devices here. It's gone a little bit further. Right, that's what you call an insulator, an outdoor insulator. So these are high voltage conductors, and they cannot physically transmit or distribute without being insulated from Earth. We all know what happens if you touch 230 volts, then touch Earth. You're going to have a high current, you're going to get a shock. So these are used to physically separate the high voltage from Earth. You'll notice that it's also elevated. Again, that's to avoid anybody touching it, to avoid a truck touching it, etc. Right, this device here, it looks like a big metal box. Inside that big metal box, there's a medium voltage transformer. Right, so we can't see much of that, but you would have studied that in Design 3, what goes on inside there. Right here is a bushing. Right, so somehow we need to get the high voltage out of the transformer onto this conductor. It doesn't look like a very big gap between the conductor and the hole there. So the bushing is used to insulate the conductor coming out of the transformer. It prevents the conductor touching anything. It is a mechanical thing, so it is mechanically keeping that conductor stable. Another note about that is that I don't think you've designed, they're designed too stringently, but on the bigger transformers, there's some grading of the electric field in the bushings. On the bottom here, we have surge arresters. Now those would be used, we'll discuss those in high voltage too, in a bit more detail. Right, if we go down, there's your low voltage supply. Right, so that actually just looks like just a bit of context for high voltage. We'll come back to it again just now. Right, so the need for high voltage comes from the need to transmit more power. Right, so we know that for the same power transmitted at a higher voltage, the current will be less, and therefore the conductor losses are less. And we know that equation quite well, I squared R. So R would be the resistance of any of those overhead conductors, and I would be the current through it. The surge impedance loading, that's something that you may have done in power systems. So you can transmit more power if the voltage is higher. So you could have a line with the same impedance, If you keep on increasing the voltage, you can increase the power transmitted on the line. So high voltage, again, it involves voltages above 1 kV. And high voltage engineering involves the design, manufacture, and testing of insulation materials that allow us to operate at high voltages. Right, so if we're operating at high voltages, we know that there are going to be high electric fields. So the high electric fields, they cause different mechanisms in insulation material than just insulating. So this may lead to breakdown of the material. Breakdown basically means that it is no longer an insulator. So high voltage engineering involves all 4 states of matter, including gas, liquid, solid, and plasma. Plasma, it can be in a gas or a liquid. It's normally a quasi-neutral state of matter. So we'll tackle that a little bit in the gas discharge area. Basically, it means that you have electrons and positive ions, and they can be separate and they can have different regions. But if you look at that from like a Gauss's law, where you look at an entire area, it will appear to be neutral. Right, an excellent example of high voltage engineering that contains all these states at some stage is the transformer. We looked at that in that video. So it'll have gas insulation. There'll be the air on the outside of the bushing. Inside the transformer, as you know from design 3, you've got transformer oil and paper. Right, so there's your solid and liquid insulation. And if breakdown occurs, you've got plasma. Right, so here's a couple of images of breakdown. This is an insulator. Again, we'll tackle this in more detail in high voltage 2. There's your solid insulator, that's non-conductive material. There's your high voltage corona ring, and there's your high voltage end bit. You can see on the surface of that conductor, there's a slight blue glow. What's actually happening there is that there's a high electric field and there's a little bit of conduction on the surface of that insulator. You can see these blue little streaks between the corona ring and the first, what they call a shed. That's actually breakdown in air. Right, so we try and prevent that from happening. Right, let's look at a substation. Right, on the right there is a transformer and it's got all various pieces of equipment in between. You may have seen these on a circuit diagram in Power Systems 1. There's your circuit breaker, for example. There's a CT, for example. You'll notice that everything's elevated, everything's got lots of insulation, etc. There's a bigger transformer. That'll be a 132 to 33 kV. Again, it doesn't look like, we can see inside, it just looks like a big enclosure of metal. but there's a lot of engineering that has gone into this. So what are the consequences when we get things wrong? This is an example of the consequence of an oil type circuit breaker not operating correctly. Basically, oil is in a container, this enclosure here, and then two electrodes move apart in the oil. And if it doesn't operate properly, an arc will form, it'll generate heat, it'll generate gases in the oil, it'll explode, and you'll basically cause a fire. This will then damage all the other components in a switchgear room or a substation. This is an example of a cable that got it wrong. So you won't realize it, but you've seen cables in one of the other pictures. There you've got your conductor in the middle, and then you've got various layers of insulation. This was a paper oil insulation. You've got a sheath, and basically you can see that it faulted and it burnt. If anybody's from Pietermaritzburg, these are from the fault that happened in December that caused a big outage. There's another example of what happened when it went wrong. At the top there, I spoke about a bushing. In this case, the bushing actually arced and exploded. You can see that the bushing is no longer there. You can see all these black streaks down the side. That's caused by damage from a fire and from oil. Right, so I hope everybody reviewed the electric fields. It's something that's quite important here. We're not going to go through all of this today. I want to talk, some of this is quite complicated, so I need a full session for this. But let's talk about conduction and breakdown in gases. We're aware that air is an insulator. If you think about it, it's not conducting. Right, so you don't get shocked by being near electric wire. You get shocked by touching it. Nitrogen, it's an insulator. SF6, this is called sulfur hexafluoride. It's a very good insulating gas. Unfortunately, it's pretty disastrous for the environment. So a lot of manufacturers are moving away from SF6. CO2, it's quite a good insulator. It's not as good as SF6. It's not as damaging to the environment as SF6. So an example of breakdown in air, we've all seen it already. You've all seen this, right? So basically in an electrical storm, you've got your Earth at the bottom here. Your clouds are like a big electrode, and then breakdown occurs between your high voltage clouds and your Earth. So that's an example of a gas discharge. So in some cases, air is conductive. Right, I'll go through this in the next lecture. There's quite a few charts that we need to go through to understand as well. Right, are there any questions about generally the